So welcome to my presentation to see how 3D printing can contribute to sustainability in manufacturing. So first, if you look at the big picture, so our CO2 emissions are growing, and they are growing quite fast. And this leads to the global warming, which will be a big threat in the future and already. On the other hand, we are also generating more waste than ever. So if you want to maintain our average standard of living, we need to really do something. So if you look where to focus, so this is based on more than 10,000 environmental product declarations. So where those CO2 emissions are coming from different products. And there, the installation phase is around 4% of the emissions, use phase around 6%, and the end of the life phase is around 4%. But then what is the biggest share? The biggest share is the production. So 86%, and that's a huge. And then if we dig up more to see what's inside of this production. So it varies based on the different products that we are looking from. So if you look at basic construction materials, there this raw material has more than 90% of the emissions. In metals and metal products, it's around 60%. And the manufacturing there is about 35%. In electrical components, the raw materials are around 40%, transport about 20%, and the manufacturing around 40%. But what's common to all of these, it is that actually it is how much raw material we are consuming has the biggest and very significant effect to our emissions. And now if you look what's the 3D printing. So 3D printing is a process where parts are made layer by layer basis by adding material and adding material only where we really need it. So we can grow the parts and put the material where we need it. This is a schematic of a laser powder bed fusion process, where we are using laser to melt, example, metal powder to the build plate. And then when we have melt the area where we want the part to be, one layer of the part, we can recoat new layer of powder and melt the next layer. And then continue this process until our part is ready. And where we can use this 3D printing to have a more sustainable future. So actually we can make better products and processes. This is a digital manufacturing technology, so it has a certain advantage. We can also make more lightweight products. Also, because this is a layers process, so we can have this in situ process quality and healing. So we can check what's happening in each of the layer, and if something goes wrong, we can try to fix that in the next layer. So having zero defects in our parts. In addition, or what's the problem with this process? It is that it's actually a rather slow process. So we need to increase the speed, and I will demonstrate one way to increase the speed. And in future, we will see much more smart and intelligent part where we combine different features in one part, and we can reduce the amount of part that we need, and we get the data from our parts. So better products and processes. So this is a computer tomography image from the back of the head. And what's happening there? So this left eye orbital floor has broken, so bottom of the eye. And what we can do with this data, we can actually generate 3D model out of this data. And then we can use this 3D model to digitally design what kind of personalized implants we would like to have there. Something like this as an example. And why to have this kind of network structure in the medical field? This is actually where the cells and tissues could grow through here. So it will integrate better to the surrounding tissues. In addition, it's more lightweight, so it's not so sensitive for hot and cold temperatures as an example. And this, how it looks like if you put that in the base and bony structure. And this part is also going around in the audience, so you can see by your own hands how it looks like. So this is one example from better products and processes. Then if we look more lightweight, even that implant was a lightweight structure, so let's go this kind of industrial parts. So this is a parts from a valve body, and then there is a bracket which is holding that. So that bracket weighs around 230 grams. And that is made by casting and machining. But then if we do so-called topology optimization and try to see where we really need the material, we know the forces that it needs to handle, and we can optimize. Let's remove all the material that we don't need there. And actually we can cut almost half of the material away. And then we can use 3D printing to manufacture this part. In situ process quality and healing. So now if you remember the schematic of the laser powder bed fusion process, so this is a picture from top of that powder bed. And what we can do there, we can have a different kind of monitoring system. Normal cameras, infrared cameras, and so on, to monitor what's happening in each of the layer. And then we can use, for example, artificial intelligence to detect different kind of defects. So we know what's the quality of parts when they are ready. We don't need to check them anymore. And what is actually much more interesting in the future, it is that we can try to heal the parts. So if there is some defect, we can tune the parameters for the next layer so the defect will be fixed. And therefore there will be zero waste and we have 100% quality. High production speed. I say that this process is slow, and actually it is a slow process. So we are melting metal powder with the laser. So what we have done here, this is from an aluminum alloy. And what's the problem with aluminum alloy? It is that it's quite reflective. So the laser beam reflects from the aluminum powder, and then only part of that energy will go to the melt of the powder. And what does it mean in practice? We need the high powerful lasers, and we need to go rather slow with the laser. But actually, if we do a little bit trick, so we tune the material. We put there some nanotitanium particles there. And why? Actually, that will affect how much the powder will absorb the laser energy. When it's absorbing more laser energy, we can go faster speed. So we can increase the build rate, as you can see in the image, and still having very good quality out. But on the other hand, this addition also increases the mechanical strength of the parts. So if we drop the speed a little bit, we can actually make stronger parts than before, but still with a rather higher speed than anyone else before. Smart and intelligent parts. So in future, we will see more parts that are integrated and having multiple functions in the same part. So there is no assembly or anything to put those parts together. They are made in a one run. Here I would explain you one different 3D printing process. So this is called material extrusion process. And in here, we have a thermoplastic filament, and we are feeding that to the nozzle, what we are heating and position. This is the most common 3D printing process, and if you have seen 3D printers, this is the most likely what you have seen. But we can actually put there another head, a little bit different head. We still have a filament that we are feeding, but now we are feeding from the side. And from the top, we are actually feeding carbon fiber wire or different kind of metal wires. And with that, we can add their continuous wires into our part. And if you look what these kind of parts could look like, so this is a flat part where we have put copper wire going back and forth. And what's the point of that? If we start bending this part, the resistance of that wire also changes, similar as in the strain gauge. So actually we can sense how much the part has deflected based on the change in the resistance. So this part has a self-sensing feature. From the nature is very cool of creating different kind of things. So if you look about the chameleon, which can change its color. In the other side, there is this kind of desktop printed digital display. So it's counting numbers from 0 to 9. And how is that made? We have a thermochromatic material which changes its color when it's reached certain temperature. And we are using those wires to heat the display and control this. So we can make parts which can change their color, and they are just a single part. They are not the assembly. Also, if you look at the human hand or muscles of the human, those are actually very interesting and fascinating, capable of doing multiple different kind of movements. So this is the concept of artificial muscle. So now we have a soft polymer, but now we are embedding their shape memory wires. And those wires will remember the position, or we can program their position and control them with the current. And we can embed their multiple wires. So we can have the movements in different directions. And now if you remember the self-sensing feature, we can also use the self-sensing feature here. So we have an actual control, and we have also self-sensing here. So it knows where it is, and we can do movements with that. Then if you think about the impact. So as I said in the beginning, so production is generating 86% of the CO2 emissions. And then let's take this metal and metal products as an example. And there the raw material was around 60%. So if we put that together, so it's about more than half of the CO2 emissions of that product. So if we would do something, let's assume that we reduce the weight of the part with the help of 3D printing as an example by 30%. What does it mean in practice? Actually, we decreased the 16% of the total CO2 emissions. So thank you.